So Matt, once I have this like recording in my Zoom cloud, how do I make that available to everyone? You put it in like a YouTube playlist?
Yeah, I put mine in a YouTube playlist. I don't know how I can give you access to like, if you post it on YouTube, I can add it to the playlist as well.
If I like just send you like a downloaded version of that video, like email that to you, would that work also? Like you could just upload the files.
Yes, that also works.
It
Okay,
might be easier if you share the link and then you can download it so it doesn't, because sending a massive video over email.
Oh yeah, that's true.
Yeah.
Yeah, that's fair. Yeah, you're welcome to do that.
All right.
Otherwise, so all I did to upload it to YouTube was I like used the UCLA Google account to create a YouTube account. And then if you just verify it with like your phone number, you can upload it. Because you need it verified to upload anything over 15 minutes. So
Makes sense.
Either or, if you send it to me, I'll upload and add it. And if you upload it, then I'll add it to the playlist.
I think it makes the most sense to just have the videos all in one place. So I'll send it to you.
That works.
Thanks. Okay, I guess I'll get started and maybe people will show up. So today's section is 1.2 of Hatcher. This whole section is on what's called Van Kampen's theorem. And this is like a big, powerful theorem that's actually going to let us compute a lot of the fundamental groups that we're looking at. So last week, we defined, what is a fundamental group? How do we compute the fundamental group of a circle? But we actually had to go through quite a bit of work to even do just that. Like you think just a circle is a pretty simple kind of shape, but it took like a decent amount of legwork just to prove that it's the set of integers is the fundamental group. And I think there's a note in Hatcher where he says something like, it's really easy to show that a fundamental group is trivial, but it's really hard to show that a fundamental group is non-trivial, or at least without Van Kampen's theorem. So this theorem is going to be like our biggest tool for actually, computing some of these groups. Like on the qual exam, if you see a problem that asks like compute this fundamental group, it's almost certainly going to be you use Van Kampen's theorem or you use some corollary of Van Kampen's theorem for like a CW complex. So this is like, I guess, a pretty big class of problems that we can now solve. So I have like a little moniker here that this is basically like non-abelian Meyer-Viederis, and that the main idea here is kind of the same. So if we start with some topological space, we want to know what is the fundamental group of this space. And to do so, we first decompose this space via some kind of open cover. We look at the fundamental groups of each element in this open cover. And then we have some algebraic way of like gluing that information back together. In the case of Meyer-Viederis, this was in the form of like an exact sequence in terms of like, here's the Theorem cohomology group of the intersection. Here's the direct sum of each of those pieces separately. And we had an exact sequence that connects them all together. But for Meyer-Viederis, the algebraic relationship we have instead is what's called a free product or a coproduct in the category of groups, but you don't quite need to worry about that. So what else do I have here? That was everything I wanted to say at the start. So the first thing that Hatcher goes over is he defines what is this mysterious free product? What is this algebraic tool that's going to let us connect all this topological information together? So, oh, by the way, this picture I have drawn here is a Van Kampen. Okay. So free products. Thank you. So the idea of a free product and what we're going to be doing with it, it's a little bit similar in terms of how we use it to, say, the tensor product from 225A. What I mean is that we start with some like really ugly looking, messy algebraic relationship. For the case of the tensor product, it was, you're quotienting out this direct product by all these linear looking relationships. And you don't like this really ugly definition. But then you show that the really ugly definition has what's called a universal property. And then from that point forward, we mostly only care about the universal property, and we never want to go back to the ugly definition. So free products are kind of like this in a sense. So the idea for what we want a free product to be is that it should be, we're going to use this notation. I'll say G1 star G2 is we want it to be the freest group generated by G1 and G2. So what do I mean by freest? Like for a group to be generated by G1 and G2, it just means if you take like the images of the elements of G1 and G2, that should generate the group. But by freest, I mean you're not imposing any more restrictions on the structure of this group than necessary. So you might, it might be nice while I tell you about what a free product is to compare this to the direct product, G1 times G2, something maybe a little more familiar with. These are in general not the same. So in the direct product, this is still generated by G1 and G2. Generated by G1, G2, but it is not the freest such group. And the reason for this is if you consider the elements, G1 comma 0 and 0 comma G2, these will commute in the direct product. And in the free product, we're going to show that these don't commute. We don't want to introduce this extra relationship of these two elements commuting with each other. We'd like it to be as just pure and no extra structure as conceivably possible. And that almost always means that the free product of two groups is going to be non-abelian. So free product is not the same as the direct product, but I'll show you later that there is a kind of relationship that they share. So what do I have next? Okay. So free products are usually defined in terms of words that can be spelled out from elements of the group. Defined by words in G1, G2. What this means is that, so if G is generated by S, which is just some subset of G, then every element of G can be written as, say, S1, S2, S3, S4, S5, where all the SI are in our subset S. So this long chain I have here, that's what I'm just going to call a word. It just means a big string of a product of some elements, and these elements are going to be within what we are generating subset. A word is just it's a word in the sense that it's a big string of letters. So in our particular case, we're going to say that we want G1 star G2 is generated by words in G1 disjoint union G2. So every element in this free product can be written we'll say G11, G22, G13, G24, G15, blah, 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 where the lower index is which group they were originally from. So every element in, we also allow inverses elements of S. Yes, sorry. Also allow inverses. I'm trying to not spend too much time staring at the details of the free product construction because Again, once I show you what the universal property is, we kind of just forget about a lot of this. But yeah, we do technically require that in order for this to be like a well-defined kind of group structure, that we have to allow for inverses of some kind. So if G1 star G2 is generated by all these words, it's worth noting that this is not in general unique word for S, a subset of G. So for some arbitrary generating subset, this way of writing out every element as a word in S, that's not necessarily going to be unique. So for example, in the example I showed above, we have that, 1, 0, and 0, 1 generate Z cross Z, but 1, 1 equals 1, 0. Whoops. 0, 1 equals 0, 1, 1, 0. So these two words right here, they are technically like different if you look at them as words, but they are actually the same group element in the direct product, which is just another way of saying that the direct product is not like totally as free as it could be. So in order to make this this free product the freest group generated by G1 and G2, like I said, we want to cut out all these extra relationships. So we're going to try to make this representation as a word in G1 and G2 unique as much as it can. And this is where the idea of we still need to consider inverses is going to come in. So I'll write that down. In G1 star G2, we do want uniqueness as much as possible. So if I can write out, any two words from G1 and G2, then they should be distinct if they look like different words. So that would be the way of saying that this is the freest group generated by these two. The slight technicality here is that this isn't totally possible using the group axioms, because we have that, the identity element is equal to G1 times G1 inverse. So we do have this non-uniqueness that's going to be created by, well, we can write the identity element in so many ways by, multiplying an element by its inverse. And therefore we can write, any element, say A equals A G1 inverse non-uniquely. But if we account for this fact and say, okay, if you give me any word, say, so this is going to be solved if we reduce our words. So if you give me a word that looks like G1, G2, G2 inverse, G3, G4, you can show that this has a unique representation as a reduced word, which means G1, G3, G4. Anytime we see an element and its inverse next to each other, we just, multiply them together, forget about it. So now if we agree that every word that we write out in the free product of big G1 and big G2, every word in G1 star G2 has unique reduced form. So the technical construction of this free product, or of free groups in general, it involves, saying, give me a word, we define some kind of equivalence relation on all of these words. Two words are equivalent if and only if there's like a sequence of reductions or like unreductions that connects one to the other. And you can show that each equivalence class of words contains exactly one reduced word. So it's often just easiest to say the free product of G1 and G2 is the set of reduced words on G1 and G2. So we need to be a bit careful here because, let me just write that out. G1 star G2 is the reduced words on G1 U G2. So I say we want to be a bit careful here because we need to take a look at what the group multiplication structure is. Because if I have something like what is G1 G2 times G2 inverse G3, well, as an element of G1 star G2, this is going to look like G1 G2 G2 inverse G3, which is not reduced. So we need to agree then that if we're defining the multiplication structure on this free product, we need to agree that we first concatenate and then reduce. So the reduction of a product of two reduced words is not guaranteed. So our multiplication must have a reduction that follows after. So the operation on G1 star G2 is also concatenation followed by reduction. Just to make sure we get back into our class of reduced words. And by the way, one can show that this like operation of multiplying and then reducing, that actually is associative, and you can probably guess what the identity and inverse elements are going to be. So this is still a well-defined group. So G1 star G2 is a group. And in general, we can define free products of more than just two groups. We can similarly define, I'll just say free product over the I and I of the GI. You know, a free product of arbitrarily many groups might look like we have a word or a reduced word with each element is from one of our original groups. So that's what the free product is. This is a kind of messy algebraic construction. Any questions at this point? Okay. So move on then. So now I'll talk about the universal property of the free product, because as you might guess, these kind of sequences of words and word reductions, that's not a particularly topological idea. So it's not something that we can directly apply to algebraic topology, but we're going to show that these free products have a universal property, which gives us morphisms of groups under certain conditions. And that is going to let us tie this into the discussion of fundamental groups that we've been having. So the first thing to note is that we have canonical inclusions from each GI into the free product of, well, I should probably change it to C's here. So what this means is that if you give me, any of our original groups that we're taking a free product of, we can just map the element, GI in GI. It's going to go to the reduced word, which is just a GI. We can include all of our original groups into this free product. This is actually going to be these canonical inclusions are actually this seems like a trivial statement to make, and that's saying we can review the original elements of our groups as reduced words, but this inclusion map is something that we're going to be using with the fundamental groups later. So it's important to take notice of. So what is this universal property I keep talking about? Suppose that there exists a group we'll call A, and there exists group homomorphisms, say Fi from each GI to A. So there's some fixed target group A such that every one of the guys we're taking a free product of has some morphism into that target, the same target for each of these groups. All I. Then there exists a unique F from the free product of the GI into A such that F of, say this is the IF inclusion map, Fi. So this looks like a lot of symbols and kind of like alphabet soup, but it might be nice to draw the universal property diagram, which is usually invoked here. So let's say I have the free product of my two groups, G1 and G2, and here's my target guy A down below. So my first map that I talked about was, F1, just some morphism from G1 into A. Then I have F2, some morphism from G2 into A. And I'm saying that there is a unique map from G1 star G2 into A. Exists a unique F that makes this diagram compute. So we'll say this is I2, I1. What this is saying is that if F1 is defined on G1, it takes each element of G1 to some element in A. But if I first include G1 into the free product, if I consider the G1 elements as G1 star G2 elements, and if I then take F of them, I should get back the same thing. So including into the free product doesn't change where the G1 elements go. So including into free product doesn't change image. And maybe this looks like a kind of weird, abstract, nonsensical property to have, but because, in topology and algebraic topology in general, we're all about, finding morphisms between different things that preserve different kinds of structure. Inclusion maps come up a lot, and this property turns out to be a lot more useful than, the reduced words in the free product. So these morphisms, or this particular induced morphism, is going to be what lets us compute fundamental groups in Van Kampen's theorem. So scroll a little bit. So now I want to compare the free product to the direct product again. Compare star 2 times. So in Z cross Z, I'll label these as Z1 and Z2 just to keep the indices separate. We have that 1, 1 times 1, 2 is equal to 1, 2. Well, I guess I should make this a plus operation. Plus 1, 1. Just because the two components of a direct product are going to commute with each other. But in Z1 star Z2, 1, 1 star 1, 2 is not equal to 1, 2 star 1, 1. This is more or less what I said at the beginning, but it turns out that there is, a more precise relationship we can find between these two groups. So so the direct product there, we can view that as a target of each of our sets of the integers, right? So we're going to use our universal property and get a morphism out of the free product into the direct product. So there exists some inclusions of our first set of integers into the direct product. Z2 into Z1 times Z2. And this is just, the element M in Z1 is going to go to M comma 0. The element N in Z2 is going to go to 0 comma N. These are the inclusions you expect. So now if we use this universal property up here, there exists a unique F from Z1 star Z2 into Z1 times Z2 such that we'll say F of M1 equals, forget that, M comma 0 and F of N2 equals 0 comma N. So this morphism that we found from the free product into the direct product, it's going to preserve this inclusion, just as I mentioned before. And what's important about this is that if we consider the fact that Z1 and Z2 generate the direct product, this means that F must be surjective, since Z1, Z2 generate Z1 times Z2. And what this gives us is, by the first isomorphism theorem, that Z1 star Z2 over the kernel of F is actually isomorphic to Z1 times Z2. So the direct product is actually always a quotient of the free product. And in general, this is going to be, some non-trivial quotient. The kernel is going to be some non-trivial thing. But this is just, an example of how do we use this universal property? How do we take a quotient of a free product, etc. And this construction that I have here, where I found a morphism from the free product into the direct product, that's, not just true for the case of Z1 and Z2. This is true for any free product or direct product of groups that you want. This just follows from the fact that the original groups will generate both the direct product and the free product. Okay, so now that's the end of my discussion on free products. I'm about to actually start talking about topology again for Van Kampen's theorem. Oh, is it generally true that the only relations in the kernel would be that the two components need to commute? This feels about right and works for Z. In this case, it is actually true that the kernel for this map is the one that makes the element in Z1 commute with the element in Z2, and I think that is true in general. All you need to do is make the elements from each group separately commute with each other. This actually is, so you might think this is not that important of a question. It actually turns out to be something that will be true later on when we get to how do we actually construct like topological spaces with the particular fundamental group. So knowing how to work with these group relations is something that's going to come up. But I think it is true that the direct product is the abelianization of the free product. I think that is true. Okay. So now back to technically you only mod out by first component commutes with second. Okay, yeah, so we're making the generators of our original groups commute. So it's not, I don't think it's the real abelianization, but we're making it very abelian, or as abelian as we reasonably would want to. Right, so sorry, in the case of Z1 and Z2, it's the abelianization, but not in general, you're right. So now back to Van Kampen's theorem. So we want to be able to use this induced map from the free product of groups into whatever group we want in order to commute some fundamental groups. So before I formally state Van Kampen's theorem, I want to show you what can go wrong if we don't make a lot of the assumptions that we're going to see. So first, let X be a topological space and decompose into an open cover. We'll say A alpha. And what else? Oh yeah, there exists a base point, say X naught, contained inside each A alpha. So the intersection of all of these A alphas is non-trivial. There's some base point within the intersection so that we can, look at loops in any particular cover as being something about X naught. So for each of these AI, there exists an inclusion map into X, right? Just by saying, okay, view this open set A alpha as a subset of X, we have an inclusion map. And by functoriality of the fundamental group, there is now a map from the fundamental group pi1 of A1 into pi1 of X. Well, sorry, that changed indices here. Pi1 of A alpha, pi1 of X to be F alpha. So I want to note that this map is not necessarily injective, even though the inclusion was, but more on that later. We just have some map from pi1 of A alpha into pi1 of X. It takes a loop class in A alpha to the class of those same loops in X. So now, since this is true for every A alpha, we can use this universal property that we had before, because now pi1 of X is a common target for the fundamental group of each of our A alphas. So by the universal property, we have a map from the free product of all of our fundamental groups, F into pi1 of X. So more concretely, so what exactly does this map do? It is more or less an inclusion of a composition of loops. So if we have, say, L in A alpha 1 times, how do I want to write this out? Yeah, okay, so L in alpha 2, 1 times L3, alpha 3. So this is going to be our element in our free product. We just have, some loop from A1 times some loop in A2 times some loop in A3, just some word of loops from our cover. This gets mapped to the class of the composition of the loops in X. So we're still traversing like the same loops that we had originally, like in the same order. It's just that we're now viewing their like class in X. This map is actually pretty concrete. It's not like some mysterious unique map. We know what this map is. So it looks like we already have a lot of information about computing the fundamental group of X, right? I showed you we have this morphism from the free product of the fundamental groups of the A alphas into the fundamental group of X. And I showed you that this is a very nice kind of map where we know what it's going to do on basically every word. But it turns out that this is not sufficient in order to be able to compute what is the fundamental group of X, which was our original goal. And there are two reasons for this. There are two reasons why we can't, why this isn't quite enough. Firstly, this map is not surjective unless we make some more topological assumptions, and it is also not, in general, injective either. So let me give you some examples to show why this is the case. So first case, to show that it's not injective, let me say X is my circle, S1. So I'm going to say that A1, I'm going to cover this in two sets. I'm going to say A1 is the whole circle. A2 is also the whole circle. So A1 and A2 are both like themselves a cover. A1 equals A2 equals X. So if I consider what is F from pi 1, A1, star pi 1, A2 to pi 1 of S1, you should note that F of, I'll say M1 is equal to F of M2 equals M. Meaning if I start with a loop that goes around the circle M times, that's going to be a loop class within both A1 and A2. So if I first include my M loop into A1 and then map it into pi 1 of S1, I'll get the same loop back. But if I also consider this loop as an element of A2 and then map it into S1, I again get back the same loop. And this is not injective because in the free product, these are not the same because they came from different groups. In the free product, we considered each of our components to be like separate things that shouldn't have different relationships between them. And in particular, their elements are very clearly distinct except for the identity element. So even though like topologically, we know these are the same loop, algebraically, they are considered as different elements within the free product, which means that this map is not going to be injective. So the problem for this case was that the intersection of our two elements of our cover is too big. Like they probably shouldn't both be the whole group anyway. This is a little bit of a silly example, but in order to make this as injective as possible, we would like the intersection of our elements of our open cover to be relatively small, so we don't have such a gigantic kernel from our induced map. So the second case I want to look at is another one we can see on the circle. Say this is X. So now I'm going to say my open cover of the circle. A1 is going to be our like upper half plus epsilon. A2 is going to be the lower half plus epsilon. So now we have, I'll say that's A1, A2. Now we have pi 1 of A1. Well, A1 just looks like an open interval, right? So this is just 0. And likewise, the fundamental group of A2 is 0, which means that pi 1 A1 star pi 1 of A2 is also just 0. Our free product is 0 because this decomposition is into covers that are both have trivial fundamental group. But we know that that's not going to be the case on the circle, right? So 0 to pi 1 S1 equals Z is not going to be surjective. So it's not exactly obvious what the problem is here just looking at it, but I'll show you that the problem from this example was that the intersection A1 and A2 was not path connected. What I mean is that these sets intersect in two places, once on the right and once on the left. And that's two different components. I can't go from one to the other from within that intersection. And what Van Kampen's theorem says is that if we add that condition along with a few others, we are going to get back some nice properties for this induced map. So this theorem comes in two parts. One's to deal with the surjectivity, and then wants to deal with the injectivity. The surjectivity case is actually something that was proven in section 1.1 if you read it carefully. And that proof, I can maybe sketch it up for you because I notice I've been talking for like 40 minutes now. But the proof for the second part of Van Kampen's theorem, I won't prove because it's not particularly enlightening. So Van Kampen's theorem, part 1. If the set of A alpha is an open cover of X such that each A alpha contains our common base point, say X0, each A alpha is path connected, and each intersection, we'll say AI and AJ, is also path connected. Then our induced map from free product pi1 A alpha into pi1 X is surjective. So all we had to do to make this surjective is we just added in this these second two conditions here, saying that our open covers are all path connected and their intersections are also path connected. So I'll sketch out the proof really briefly. So what do we actually need to show in order to prove that this is surjective? Well, let me scroll back to my circle example here. What we want to say is that if we look at some loop in X and we consider it as like being covered by our A alpha, then there should be some way to decompose our loop in X into a product of loops, where each of our loops that we're decomposing into is contained inside either A1 or A2. So we want to decompose L in X into L alpha in A alpha, so that maybe like L alpha, L beta, L gamma, blah, blah, blah. The class of this in X is equal to the class of L in X. Because if we can do this, then remember that by the definition of our induced map, this is f of L alpha contained in alpha times L beta contained in beta, dot, dot, dot. So this would give us surjectivity. It boils down to being able to decompose our big loop in X into smaller loops that are each contained in some element of our cover. So the idea here to actually be able to do this decomposition is that given a G from the unit interval to X, there exists a partition 0 equals S0 less than S1 less than dot, 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 Sn equals 1 of our interval, where the interval between two of our points, say Si and Si plus 1, is contained in a single AI. That doesn't mean that there's like a unique AI that's contained in. It means I can find some AI that contains that whole interval, which is kind of what we're looking for. The reason for this is that there is a open ball around each G of t, which translates to open neighborhood in 0, 1. So if we decompose an open cover of our loop in X, we can translate that into an open cover of the closed interval 0 to 1. And this closed interval is compact. So if our interval looks something like this, and we can find some finite subcover that might look like this, maybe like this guy, one of these. We can find some finite subcover of our 0, 1. Then maybe it's a little clearer that if I take, S0 is here, maybe this is S1, S2, S3, Sn. Just take the Si to be the endpoints of finite subcover. Then F of the intervals like Si, say Si plus 1, is going to be contained in some AI. Oh, by the way, I should specify that the open ball that we took initially, we're restricting it to be in some AI. That's probably an important step. For each guy in the range, we can find an open ball contained inside of some specific AI. And then I'm saying that we can eventually kind of glue this information back together. Okay. So so now that I've shown that we can partition our interval kind of like this, the picture that you want to have in your head, we'll say this is A1. This is A2. Here's our base point X0. So let's start taking some loop that is not necessarily contained in A1 or A2. Maybe this is going to be L. So let me say here is a point on our original interval. We'll say that's like Si. Maybe here is Si plus 1. Here's Si plus 2. We notice that if Si is in A1 and Si plus 2 is in A2, then I can find some interval that's contained inside just A1, and then I can also find some interval on this loop that's contained in just A2. So if I travel along this loop from X0 and I hit this endpoint that's in A1, but that the next endpoint is not in A1, what I do is I just draw in the line that connects this endpoint to our base point, and then I go back, and then I just keep going around. And this is possible because A1 and A2 is path connected. So we can decompose big loop at certain endpoints in 0, 1. Because now this loop that I have in yellow is contained totally in A1, and the loop that I have in A2 is contained totally within A2. And our original loop, it's homotopy equivalent to the concatenation of these two loops here. And this is exactly what we wanted to show, that our big loop can be decomposed into a product of loops, each contained entirely within some AI. So now we know that the f from the free product pi1 alpha to pi1 of x is surjective, because every loop class in X can be decomposed into products of loop classes in our individual AI, which means that by the first isomorphism theorem, pi1 of X is isomorphic to some quotient of pi1 alpha I over the kernel of F. So this at least gives us some kind of formula for the fundamental group of X. The problem is that finding kernels of maps from a free product, or in just normal subgroups of a free product, and trying to compute what that group is, that is very difficult to do in general. Because free products, they are just big classes of words. You have to mod out by different words. It's really hard to show that groups like this are even going to be finite. And trying to compute a quotient of a free product is just something that's kind of really difficult to do. So this is where the second part of Van Kampen's theorem is going to come in. Recall what I showed you was like the double inclusion from our non-injective example. So let's say here's my A1, here's my A2, and I draw my little loop here that's contained within A1 and A2. So let's say my red loop is, I'll just call it L. It's an L. Then F of L as an element of A1 is going to be equal to F of L as an element of A2. And therefore, this map is not injective, which is basically the same thing as saying that F of L1, L2 inverse is equal to the identity. So the kernel of our map contains these elements that look like double inclusions, where we include the same loop into multiple different parts of our cover. And what Van Kampen's theorem is going to show is that under a certain extra condition, these kind of double inclusions are the only things we're going to have in our kernel. So VK part 2. Furthermore, if each a alpha and a beta and a gamma is path connected. So now we're looking at triple intersections as opposed to just double ones. Then the kernel of F is the normal subgroup generated by, say, F of L1. Well, I shouldn't say F. I should just say L1, L2 inverse, which are the double inclusion elements. So I said that all these double inclusion elements, they are where we have these L1, L2 inverse, those always have to be in the kernel. But I'm saying that if we know our triple intersections are path connected, then actually this is basically everything that is in the kernel. So once you can analyze what's going on in these double inclusion maps, if your triple intersections are path connected, then this kernel is the normal subgroup generated by these guys. This looks kind of messy, but there's actually an interesting way to thing you can get from this. So in particular, if pi1 of A1 and I'll say A alpha and A beta is 0 if our double intersections are always simply connected, then f from the free product pi1 A alpha into pi1 x is an isomorphism. So I told you it was already a surjection, but if we look at this condition here, and that if our kernel is just generated by these guys, but if these guys are also going to be basically 0 elements within our free product, then this is going to be an isomorphism because our kernel is going to be trivial. So yeah, again, I'm not going to prove this, and I'm going to go over some examples really quickly and then into some problems. Do you guys have any questions on the statement of Van Kampen's theorem or what I'm actually doing here before I start working with it?
Why again do we need the triple intersections to be path connected?
That is the proof that I'm not going to go over. And I looked at the proof in Hatcher and I saw this really weird picture with somewhat like a table of squares that were all kind of skew from each other. And that picture made me just really upset and I didn't want to read that proof. And I don't think it's helpful either. So we're not going to look at it.
I guess my question is, do you have any good counterexamples, like if triple intersection is not path connected where this is false?
Oh, not off the top of my head, but also none have appeared in the problems I've looked at. So I would dare say it's not something we need to worry about.
Cool.
Yeah, fucking Hatcher, exactly. Any other questions so far? Okay, so I'm definitely way over time here, but I think these examples are going to be good to see. So the kind of canonical example for something we want to be able to compute the fundamental group of that looks kind of obvious but isn't quite obvious is the figure 8, which is, formally this is the wedge product of two circles. But let's take a look at what we can do here. So if I were to say find an open cover and a base point for our figure 8, I would say, take our base point to be this guy at the center. And if I now want an open cover, I would just say, two sets that each contain the base point. Every one of these talks has gone 2 hours, yeah. I would maybe probably take this open cover, where there's my yellow guy. I also have a blue guy. So I'll each AI is going to deformation retract onto a circle. Because these little this little plus epsilon bit you get into the other part of the circle, you can just kind of retract those back to your base point. Furthermore, A1 and A2 is going to look like this, right? It's going to look like our base point with a little bit extra sticking out of it. This deformation retracts onto the base point. So the intersection of the elements in our cover is actually simply connected, which means that the intersection is going to have our trivial fundamental group. So if we look at pi1 A1 star pi1 A2, by Van Kampen's theorem, this is actually isomorphic to pi1 of, hold on. Yeah, this is isomorphic to pi1 of x. Because the double intersection here is path connected. More than that, it is simply connected, which means that our kernel is going to be trivial. So we have this isomorphism, and therefore we get that this is going to be z star z. So the fundamental group of the figure 8 is the free product of z and z. So what exactly do the loops in this figure 8 look like if you haven't seen this before? Well, we'll say going around this yellow loop, we'll call this A. And going around this blue loop, we'll call this B. So an element might look like, first you go around A, then you go around B, then maybe you go around A in the opposite order, then maybe you go around B again, then you maybe go around A in the opposite order again, et cetera, et cetera. But the generators of this free product are, just going around the yellow part and then going around the blue part. This is something that might be, again, is kind of intuitively clear. I think there was a brief discussion of it before section 1.2. But being able to prove that this is what we think it is relies on this kind of topological decomposition and understanding of the free product. So this example is actually a kind of sub-example of a more general thing that we can do for the wedge products. So what is pi 1 of, we'll say, x wedge y. So the wedge product is the space you get if you take x in x, y in y, identify x equals y. So basically taking two different spaces, find a point on each and join them together at that one point. And you look at the topology you get from there. So in the case above, we say that this is the wedge product of two circles because, right, I have two circles. I found a point on each of them and I stuck them together at that point. And this is something that we can do in general for more general spaces. And with basically the same analysis where we take our open cover to be, okay, we'll say A1 equals x plus epsilon, A2 equals y plus epsilon. If the connecting point has an open neighborhood that deformation retracts onto it, we again have an isomorphism. Pi 1 x wedge y equals pi 1 x star pi 1 y. And it's basically the same argument that we made before. It's just, it's a little easier to see it worked out with the figure 8. I'm going to do one of the examples for circle linking, which was in Hatcher. I don't want to do all three because just for the sake of time here. So the next one is what happens if we look at r cubed minus S1. What I mean by this is we have our big space. You can imagine that r cubed is just like a big block. And I'm going to just remove some circle from this space. So how am I going to compute the fundamental group of this? Well, the first thing we're going to do is we're going to deformation retract this space and turn it into something that's a little easier to use Van Kampen's theorem on. So via a deformation retraction, what we can do is, first we can retract like everything pretty far away from our cutout circle onto a sphere. And then we're going to cut out everything inside is going to go on like we're going to bring it close to a line through that circle. So every point we can either, map it onto the boundary of the sphere, or we can map it onto some bit that goes through the circle. Let's make it a little clear that this is like a sphere. Now what I'm going to do is I'm going to deformation retract this again. I guess this one's not, I guess it's a retract. We have our sphere, we have our red circle. And now I'm going to take the endpoints of this like diameter of our sphere in our first retract, and I'm going to pull them together So our space actually looks like S1 wedge S2, because we have this circle that is going through our red loop that's attached to a base point. And we also have a sphere which contains the same base point. So pi1 of r cubed minus the circle is equal to pi1 of S1 wedge S2, which is equal to pi1 S1 star pi1 S2 equals Z. So this is a pretty general idea that we can use in a couple of different problems, being that it's not always easy to apply Van Kampen's theorem straight away. But if we, oh yeah, can you explain the picture a little bit more? Yeah, so the first picture is the space we're starting in, where we have, r cubed minus a red circle. So we, cut out the circle. We have every point in R3 except for the red circle. Then we deformation retract this onto a sphere where, everything really far away from our circle goes onto some sphere around the circle. We'll say the center of the circle is the center of the sphere. And then you can imagine that, all this stuff that's like inside the circle or reasonably close to it, we can like squish it down onto the axis near the circle. Or anything that's arbitrarily close to the circle, we can either push it outwards towards the sphere or push it inwards onto the axis. So now we have a sphere plus diameter. Then in our next step, all we do is move the endpoints of diameter. Josh, does that make sense? What step is like less clear? My art skills are not so good.
I think your mic is quiet again.
Okay, you think you got it. Okay. But yeah, the idea is we can just take a deformation retracts and we can either then apply Van Kampen's theorem straight away, or we can find something that we can deal with using a corollary of Van Kampen's theorem, in this case being the wedge product one. One more example that, well, I guess my next example will lead into discussion of CW complexes, because we want to be able to do some stuff with that. So first, we're going to compute the fundamental group of a graph. Yeah, I'm claiming that we can actually compute the fundamental group of any, say, finite graph, but actually will, I guess, for any graph in general. And as you recall, a graph is just a one cell where you have vertices and edges connecting them. So the example I'm going to show you is not the one that's actually in Hatcher. I think this one might be a little easier to see what's going on. I have this like orange slice graph, if you want to call it that. So if we wanted to start decomposing this, the way you want to look at it is you first want to find a spanning tree. A spanning tree meaning, take some take some tree of your graph that hits every vertex. So the one I want to use is this one. This yellow shape is a tree and every vertex is contained in it. Now, for each EI not contained in T, we'll say our tree is T, let AI be an open neighborhood of TUEI that's deformation retracts onto TUEI. So what I mean is this. So in our graph here, this edge in red is not contained in our tree. So what we're going to do is we're going to find an open neighborhood of the spanning tree and our extra edge that is more or less going to look like the spanning tree plus our extra edge. Draw this in here. So there's our tree. Here's our extra edge. In the open neighborhood I'm going to take, we take every edge that I just said, and plus epsilon into each of our adjacent edges. Blue is AI. For our red edge AI, the open cover we take is this blue guy here. Then, if AI is not equal to AJ, so if we take the distinct pieces of our cover, then AI intersect AJ, deformation retracts onto T. So if I drew in like another one of these AI in this picture, I wouldn't have the entire red edge in that second AI, right? Because that red edge is only contained in this one AI. So if I now intersect my AI and AJ, then I won't have any whole edges that aren't in T. I'll have a little bit of plus epsilon around every edge that I can now deformation retract onto T. And I also want to note that AI deformation retracts onto a single circle, or in this case, a triangle. I also want to note that T is simply connected, being a tree. So by Van Kampen's theorem, we have our open cover consisting of AI for every edge not in our tree. Their intersection is path connected, but more than that, we know that it's actually the intersection is going to be simply connected. And we know what the fundamental groups of each element of this cover looks like. We have that star I of pi 1 of AI is isomorphic to pi 1 of, call it our graph G. And this guy right here, because each of our AI deformation retracts onto a cycle, this is just going to be a bunch of Z's. So for our specific case, this is actually going to be, how many Z's do I have? So I have, looks like I have 1, 2, 3 edges not in my graph, or not in my tree. So this is going to be just this. I have 3 AIs, 3 edges not in my tree. So so Van Kampen's theorem gives me Z times Z times Z. There are essentially 3 different kinds of cycles in this graph. So let me show you concretely why you might want to believe that this is actually true. So if I look at my entire graph again, here's my here's my spanning tree. Here are my 3 edges that aren't in my tree. You can imagine deformation retracting all of these red edges into a single point, and then you will get something that looks like this. If I shrink all of these red edges, I will get a wedge sum of 3 circles, which maybe convinces you that this is actually the correct computation. The generators of my fundamental group, it's choose a circle and then go around that circle. So this is something that's going to work for basically every graph, in that it's 1 copy of Z for each E not in T. So the algorithm here is, first you find a spanning tree, you count how many edges aren't in that tree, and then you just take a free product of a bunch of z's for each of those edges. And again, and like visually, it boils down to you can deformation retract along all of those edges and get something that looks like a bouquet of circles. But Van Kampen's theorem, again, lets you kind of prove this formally. So another example you might want to look at, you might recall from like a week or two ago, there was a problem involving like, this is a Hatcher problem. You had like a box with like different sides and edges identified and ended up being like based on like the quaternion group. And I did not really understand what he was doing at the time to go through that problem. But he ended up showing that the one cell for this graph, it is 2 points and 4 edges, right? A, B, C, D. So in this particular graph, I would say my minimal spanning tree is this one edge. And therefore, the generators of my fundamental group are going to be, I'll say, a B inverse, a C inverse, and then a D inverse. So the fundamental group of this graph with 2 points and 4 edges is also going to be Z star, Z star, Z, which we can again see with this essentially the same algorithm. So this was how we compute the fundamental group of graphs, which are, one cells where we have just points and edges. But we would like to be able to use Van Kampen's theorem to now compute what is the fundamental group of a more general CW complex. And it seems like we should be able to use this algorithm that we had for the one cell. Like if we know what the fundamental group is for a graph, and then we stick some 2 cells or 3 cells or higher on top of it, it seems like we should be able to compute what is the new fundamental group based on what we had before. So how to compute I1 of X for X a CW complex. And the answer is in the form of grouped presentations, which I will review for you. So suppose I have a graph G with a fundamental group, pi1 of G. I attach 2 cells to G around loops, we'll say L1, L2, blah, blah, blah. So what is this going to look like in our graph? Let's say I have our familiar figure 8 graph. Here's our generator A, here's our generator B. We'll say that I attach my loop to, or attach a 2 cell to the loop. I think I want A, B, and then, do I have a better example here? This is what I want. Right, okay. So I attach to AB inverse. So I have some 2 cell whose boundary is, first you go around A, then you go around like B in the opposite order. So it's a little hard to visually look at what this is going to be, but we can show that's going to look something like, our fundamental group was originally the group generated by A and B freely. In terms of presentations, this is going to become AB inverse is E. What I'm saying here is that if I attach a 2 cell and its boundary is, some composition of generators of our original fundamental group, then that 2 cell is going to take that sequence of loops to 0. Oh, here's my easier to see example. I should have started with this one. So consider our circle S1. Now we know our one generator is just, go once around the loop. We'll say that's A. And suppose I turn this into like a cup shape by adding in a 2 cell that looks like this. This should be much more clear. So now if I go around this loop in my 2-cell, it's easy to imagine that I can like shrink that loop down to the point down here. So adding 2-cell to loop A sent A to, we'll say 0. If we attach a 2-cell to a loop in our original graph, like at the boundary of this 2-cell is some loop in our original graph, then we can, pull that loop along our 2-cell onto a point. So in our new fundamental group, that particular loop is going to go to 0. And here's the kind of example that I have here. So theorem 1.2.6 is that for a 1 skeleton X, if we attach 2 cells to get a space Y along loops L1, L2, ... then pi1 of Y equals pi1 of X divided quotient by the normal subgroup generated by whatever your boundary is. So we start with whatever the fundamental group in our graph was. We take whatever the boundary of our 2-cell is, and we map that boundary to 0, which looks like the following in terms of the algebra. And this is something we can do by repeatedly attaching 2 cells, right? So if I attach one 2-cell, I send these loops to 0. I can attach another 2-cell, send these other loops to 0. My normal subgroup is going to be whatever is generated by all the boundaries of the 2 cells I attach. So the kernel is boundary of 2 cells. So that's the case we want to make for attaching 2 cells. But you might also ask what happens if we attach, n cells? What happens if I attach a 3-cell or attach a 4-cell? Turns out that attaching n greater than 2 cells does not change pi1. It's not entirely easy to see, but it just goes to show that the interesting structure of the fundamental group is contained within these 0, 1, and 2 cells. We can first compute our fundamental group of a graph, which we know is a free product of a bunch of z's, and then we can quotient out by the boundaries of our 2 cells. So, here's the other example I want to show you, is that if you might recall, we can define a torus to be our figure 8, say A and B, and we attach 2-cell to A, B, A inverse, B inverse. And you can show that, if you attach a 2-cell like this, it's going to be, you can like turn it into that square that has opposite edges that are identified. So this is why we say that this like figure 8 with this 2-cell is going to be the torus. The boundary of our 2-cell is A, B, A inverse, B inverse. So now I say that pi1 of t. Well, we know that pi1 of our graph is going to be, z times z. We have 2 generators. So we're going to say A comma B. And then the relation we're going to quotient out is we're saying that A, B, A inverse, B inverse is going to be the identity. Everything on the boundary of our 2-cell goes to 0. So this means that this is A comma B with AB equals BA, which is just Z times Z. So this is just another way of showing via this 2-cell construction that the fundamental group of a torus is the direct product with Z and Z. So there's a nice corollary of this construction is that for any group at all G, there is a 2D cell complex xg with pi1 of xg equals g. What I'm saying is, literally any group at all you could come up with, I can give you back a 2D cell complex that has that group as a fundamental group. Let's take a second to appreciate like how kind of incredible a result that is. Because similar results in other regions of math are either not true or are open problems. Like if I asked you, is it true that there is an like a smooth manifold that has kth Theorem cohomology group equal to this group G? The answer is no, because you can only get real vector spaces as Theorem cohomology groups. If I asked you, is there a Galois extension of the rational numbers such that the Galois group of that extension is equal to arbitrary group G? The answer is that's an open problem. We don't know. Like these kinds of questions are kind of they're either just not true or are unknown in general in math. But here I'm saying not only can any group be the fundamental group of a topological space, it can be the fundamental group of a 2D cell complex. And even more, you can build that 2D cell complex by yourself. Like you could do this right now. So the way you do this is that you say every group G has a presentation. We'll say G equals the group generated by the GI with relations Ri. So what we're going to do is we have a bouquet of circles, one for each GI, and then we're going to attach 2 cell to the loop given by Ri. And in this way, you can see that this like bouquet of circles with certain loops are going to go to the identity is going to have fundamental group of G, just based on the construction that I showed you above. And this fact that every group has a presentation, that's kind of an algebraic fact. It follows from constructing a free group on the set of elements of G. But this is something that's like, maybe you don't need to know so much as knowing that every group is some fundamental group. And if you still aren't convinced that this is a cool result, I'm going to tell you there's a qual problem in which you have to give a 2D cell complex with a specific fundamental group. So you kind of have to know this. So computing all of these like presentations of groups and working with these relations, that might not be something that a lot of you are comfortable with, because it seems like it is kind of abstract nonsense alphabet soup. But looking at the problems I've seen, the groups you get and the relations you get for like the geometry exam don't seem that bad in general. So I think what you want to know is like presentations of very common groups. So I would say that, the integers, this is the group generated, the free group generated by a single element. The cyclic group of order n, this is generated by a single element with relation a to the n. So I'm saying, take the element 1 in z mod nz, and I'm saying that add that to itself n times, and you get 0. A very common presentation that I haven't actually seen for this qual, but maybe it could come up, the dihedral group of order 2n. That's generated by 2 elements, a rotation element and a reflection element, such that rotating n times around your polygon gives you 0, reflecting twice gives you 0, and then RS is also 0. This looks like RS equals SR inverse, where we can kind of commute these elements in a certain way. This is how you would write it as a presentation. You can also find presentations for, if G is given by, say, GI and RG, and H is given by H is given by HI and RH, then G star H is equal to GI disjoint union HI, such that RG disjoint union RH. This is another way of saying that we aren't introducing any more relations when we take a free product. We're looking for the freest group we can get when we do a free product. Likewise, the direct product, G times H, is GIU HI, mod out by take all the relations in G, take all the relations in H, and then we're going to also have the commutator of GI and HI for every GI and HI. So recall that GI HI equals GI HI GI inverse HI inverse. What this commutator means, if we say that we're putting this commutator as one of our relations, we're saying that in this group we want this to equal the identity. We're saying that that element should get mapped to 0 along our boundary, which is the same thing as saying that GI HI equals HI GI. By putting this commutator as one of our relations, all we're doing is we're making elements of distinct groups commute with each other, which is what gives us this direct product. So that was the last of my bit of lectures and examples. Does anyone have any questions on anything we've seen before I just get into the problems?
Can I ask you about that? The graph example, when you had the red and I forget what color.
This one?
The 3 little train.
This.
That one, yeah. So what was? I guess the red is the intersection of the sets, right?
Oh yeah. So the open cover that you would take. So one AI is going to look like this blue guy, right?
So it's that intersection plus, I guess, a single connecting piece or something.
So the open cover we're taking is for each edge not in our tree, we draw a blue thing that looks like this, where we have T, we have our edge that we're at that's not in T, and we have an open neighborhood of that guy, like a small open neighborhood. So I have the red edge, I have the yellow tree, and I have this extra blue bit that's on the bottom here. That's our open neighborhood, right?
Okay.
So now if you consider, what if I intersect AI and, well, maybe I get a different highlighter color and make it clear. So let's look at what is the open neighborhood of this edge in orange here. I have a lot of colors now, but let's go with red. So this open neighborhood is going to look like this tree. Oh my God, that edge. And we get a little bit over here.
Oh, okay.
So this is kind of, I probably shouldn't have drawn this, but maybe you can visualize at the intersection of these two, you don't have either of your two missing edges. You just have T and a little bit extra, which deformation retracts onto T.
Okay.
And because T is a tree, it is simply connected. So the fundamental group of the intersection is trivial because you can just squish everything back down to one point. That was the key step.
Oh, so, okay. So the intersection is actually T. Yeah.
The intersection is something that deformation retracts onto T. So yeah, it's like T plus epsilon.
Oh, okay. So okay, that makes sense.
Okay, is that good?
Yeah, that's good. Can I also ask you about the S1 example where you said you can
Oh, this?
send that loop? Yeah, is the dash a disk?
Yeah, so I'm attaching a 2-cell to the boundary of S1. So this disk here is my 2-cell in 3-dimensional space, right? So it's like
Oh,
I have a cup shape now.
right?
What?
Kind of looks like a basket or something.
Yeah, like a basket or a cup. So I have this like
Okay.
cup shape, and that loop that was originally on the boundary of S1, you can imagine I just like pull it downwards now along the cup to the base of the cup. And now that loop, which was non-trivial in the fundamental group of S1, is trivial in the fundamental group of our new space.
Okay, that makes sense. Thank you.
Uh-huh. Okay, so any other questions before I get into some problems? Okay, let me start pulling up some problems then. So all the time I was wondering who Sam's tab was. Yeah, okay. S15, number 8. Okay, so first problem is going to be S15.8. So, and we're only going to do part A because part B is like homology groups, which we haven't seen yet. So let X be a CW complex with one vertex P, two edges A and B, one two-cell F1 with boundary of AB squared, and another two-cell F2 with boundary BA squared. And the problem is more or less asking you to compute I1 of X. So this problem I want to walk through myself just to again show you how do we work with all these relations and free products, etc. And also because for this particular problem, I really think that like either you are comfortable with the presentations and you can get this very quickly, or presentations still seem like kind of mysterious to you, and all these reduced words are kind of weird, and you're just going to stare at this for a while and not be sure what to do. So I don't think we need to like discuss this one in particular. I think it's just best that I show you what's going on here. So the solution here, first draw the graph of just the edges, we'll say A and B, and the point P. So we'll say this is our space Y, and we've seen before that the fundamental group of Y is Z star Z, which is the free group generated by A and B, where our generators are going to be go around A once and then go around B once. So by corollary to Van Kampen's theorem, what happens when we attach these two cells? We have pi1 of X is equal to the group generated by A and B still, but now the boundaries of these two cells go to 0. So AB squared is going to be 0, BA squared is going to be 0. And we need to compute what this is. So in general, I want to say that computing like groups from presentations is extremely difficult. But I think on the geometry exam, they're not going to give you one that's particularly hard. So the advice I want to give for like how do you deal with these like weird looking presentations, it's kind of hard to understand what they mean. My advice is try to find the order of your generators. So it might not be true that your generators have finite order in this group given by a presentation, but oftentimes they will. And once you know that, it can be really easy to start like reducing this group to something that's familiar. And it might also be worth your time to try to find commuting elements. Because if you can prove that your generators commute with each other, then you get something that looks that's going to be pretty abelian. If you can show it's finite, then you now have a finite abelian group. Those are pretty easy to work with. So these are the two tricks you usually want to use to try to reduce these group presentations to something more feasible. And this one actually turns out to be something very simple. Like you might expect that this is like a really infinite sub quotient group of the free product of Z and Z. This turns out to be an extremely simple group. And let me show you how you do that. So the first thing I see is I have AB squared equals the identity, and also BA squared is the identity. So the first equation will give me A in terms of B, but the second equation will also give me B in terms of A. So it seems like if I just combine these two relationships, I should get some interesting identity on A. No, I'm not joking. So I don't know if that's a pun on simple groups or the fact that I think the group you're going to get is like not like very complicated, but you know, it does turn out to be a simple group, and you'll see which one that is. Okay. Okay, so AB squared is the identity. This gives you A equals B the minus 2. BA squared is the identity, gives you B2 times B to the minus 4th equals B to the minus 3rd is the identity. So B has order 3. And via basically the same argument, you can say that A also has order 3. So just by using these relations we've given, we can find pretty quickly what the orders of our two generators were. So now if we take a look at our relations again and try to use this information, what do we get? AB squared, well, we said that was the identity. But now that I know that B has order 3, I know that B squared is equal to B inverse. So actually, A is B. We never had two generators. We had just one generator from the start. We could prove that they were equal. And we also have that A cubed is the identity. So our group presentation is actually A such that A cubed is the identity. So our group was actually Z mod 3Z the whole time. This was Z mod 3Z and fancy Cologne. And again, the idea here is, you know, we have some really weird looking relations, but once we can, you know, find something that kind of simplifies our generators, or just find a way to prove that this is like an abelian group or has an interesting normal subgroup, we can put it in terms of something that's a lot easier to work with. And in this case, it was easy enough to show that A and B are actually the same element, which greatly reduces this computation. So the answer here is that this fundamental group is just Z mod 3Z. And yes, that is a simple group. So any questions about this problem or working with group presentations?
I guess strictly speaking, do we have to show like also not the trivial group?
I guess technically you would need to show it's not, but I think in this case, once you can show that this, you know, our group is this, it kind of follows from the fact that this group is not the trivial group. Like we can change our statements about A and B into this, and we know that, okay, this is Z mod 3Z. And if you still needed convincing that this group here is Z mod 3Z, you can say, well, I can find a surjective homomorphism into Z mod 3Z. So you're done.
Yeah, fair enough.
Okay. Let's see, next problem on my list. So that one, I guess, is not much to discuss over. There's an interesting one. Spring 16, problem 8. So let X be the space given by, you know, 3D space, and we get rid of the x-axis, get rid of the y-axis, and get rid of the z-axis. What is pi 1 of x? This one I will open up to discussion for the rest of you, because this one I think is definitely worth thinking about. So let me just draw our space here, cutting out all 3 of our axes and trying to find the fundamental group of what's left.
Can you deformation retract that complement into like the one skeleton of a cube or something?
You actually, yes, you can do that. Although I think, could you maybe explain how you get that retraction? Because at least it wasn't obvious to me looking at this picture.
I guess, I don't know, it's not really rigorous, but like my intuition from the problem you did earlier was like, you kind of have to like, it's like two like complementary shapes, if that makes sense. Like everywhere where this
yeah.
thing isn't, it's like,
Yeah, so you're looking at, think of the linking circles example, right? Is that
yeah,
it? So like
yeah.
each of these axes is going like through the spaces of your cube. Is that what you're thinking?
Yeah, I guess.
So I guess that is one way to see it, and I'll draw out what Jacob's talking about here. And I did this calculation, and this does work. It does give you the right answer. But I think there are like several deformation retracts you could do for this problem that all give you the same answer. So with Jacob's method, we will deformation retract onto the cube. So now, does someone else want to try to compute the fundamental group of this cube?
I just realized a much easier deformation retraction to see, but yeah.
Like the cube is just S2, right?
The cube is what?
Just like a sphere.
Oh no, this is the like just so it doesn't the original space doesn't, it's not the solid cube that we're deformation retracting onto, it's the cubic graph, right? Because we can't have the points on the faces of the cube where the axes were, right?
I realized a much easier deformation retraction is just, since you don't have the origin, you could just deformation retract onto the sphere and it'll be the sphere minus 6 points.
Yes, you can also do it this way.
Okay, I believe this one. The cube thing was like miles over my head.
The cube one does work though, and I'll show that in a second. So you can either deformation retract onto the sphere since you don't have the origin, or you can go onto the cube. So let's start with the sphere one first, because maybe we're all on the same page for that one. How do you compute the fundamental group of a sphere minus 6 points?
You can stereograph a project from one of the points, and now it's R2 minus 5 points, which I guess deformation retracts onto a wedge of 5 circles.
Yeah, that works. 1, 2, 3, 4, 5. So the fundamental group is actually this bouquet of 5 circles, which is going to be, you know, Z star, Z star, Z star, Z star. There we go, 5. So this is a slightly unintuitive result, because when I first looked at this, I would have sworn it's like 6 copies of Z, but it's actually just 5.
Right, so why did, or how do you get circles and not, I guess, balls? Like, are you bringing the points all together?
So it's a little, maybe Josh, you could explain your intuition for the stereographic projection or what this looks like.
Yeah, I guess like if you consider S2 minus like one specific point, that's just R2. So now you're looking at R2 minus 5 points. And why is this the wedge sum of 5 circles? Do I remember how to do this? I guess you can just kind of like kind of imagine like expanding each of the punctures a bunch until they kind of like have to like all like get up next to each other, and then like the outside part also just kind of collapses down inwards. There's probably a better way to see this.
That makes sense. That's kind of weird. Yeah, that makes sense.
This is also just a fact I memorized, that R2 minus n points is the wedge sum of n circles.
Okay.
Yeah, that does work. So this argument of retracting onto the bouquet of 5 circles, that does work. But I want to show a few other deformation retracts you can do just to maybe get used to working with graphs. So for starters, this cube graph, again, you're correct that you can deformation retract onto the cubic graph that doesn't, you know, contain its insides. It's just like the edges of the cube is our graph. So if we wanted to do our spanning tree argument, I would say, you know, take my spanning tree to be 1, 2, 3, 4, 5, 6, 7. And now I am missing 1, 2, 3, 4, 5 edges from the cubic graph. So if I apply the same argument I showed you that works for any graph, I would say, well, there are 5 edges missing from my spanning tree. So the fundamental group is exactly, Z star 5. I'll leave the notation I use now. So you get the same answer with the cube graph. It's just maybe a little harder to compute for that one if you don't remember the spanning tree argument.
Where did the axes go on that cube? What happened?
You mean the red axes of three-dimensional space?
Yeah, like the part that's missing, or I guess just generally.
Yeah, so it's like saying that the space, we're taking anything around the axis and like pushing it outwards onto the edges of the cube. That's what it is. Does that make sense?
Kind of.
So maybe I'll take like a point right here and I'll push it onto the cube. Or I'll take a point like here or here, that'll go onto the edge of the cube.
Okay. Oh, I see. So it's kind of like you first shrink all of R3 down to a cube with a like hole through each.
Yeah, you can think about, yeah, you could do it in steps if you wanted. First you get like the cube minus 6 points, and then you expand each of those points to like eat up the faces.
Okay.
You can think of it like that too.
That makes sense.
Yeah, I was about to say you can see this from the sphere argument as well, where you expand each of these points once you like arrange them in a kind of cubic space, and then you expand those circles. But maybe that would be more complicated.
I see that, but yeah.
So one more deformation retract that might interest you. So if I again start with my sphere that has 6 points removed for it, I'm going to line these 6 points around the equator. 1, 2, 3, 4, 5, 6. And now I'm going to start like deformation retract. I'm going to expand these into like circles, right? So each of my points is now just a whole circle missing from my sphere. Now I'm going to deformation retract this guy onto, now each of these circles, it looks like this. Sorry, let me make that a bit bigger. Where I drag the top and bottom of each of my circles to the north and south pole of my sphere. So I have like a bunch of slices that were taken out of the skin of the sphere now. And now if I deformation retract this again, I'm going to get the north pole, the south pole, edges of adjacent like slices will be identified. So now I have 1, 2, 3, 4, 5, 6 edges, 2 points and 6 edges. And via an argument I kind of made already, if that's my minimal spanning tree, the fundamental group is going to be Z star 5. So again, this is by, if you instead take our removed point into a removed circle, we can kind of stretch those circles upwards and then around until we have, 6 lines going in between the north and south pole. Yeah, it does kind of look like a fruit, now that I mention it.
Quick question that you may or may not have a good answer to. For the actual qualifying exam, this argument about graphs, is that something that we can just cite? Or do you think it is, I guess?
I wouldn't, I think it's like straightforward enough because it's, used in the computation, like all the theorems about the CW complexes kind of follow from this. And I think it is fair game to just say, by the way, if we take a minimal spanning tree to be this guy, then our fundamental group is like Z star, blah, 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 for each missing edge. I would like, to me, that seems like it's fair enough game. And also because I think, in our 225B discussion a few weeks ago, it seems like our TA used that kind of freely without really working that out.
Yeah.
So I think I would be fine with it. Although the argument that you need to make is not terribly, if you needed to prove this, the argument is not terribly complicated either. So.
Right. Okay, fair enough.
We can ask Ilan next week.
It's not like topologists prove anything anyway.
Yeah, honestly, the argument here is just so weird. It seems like you should just write at the top of your page, we hold these deformation retracts to be self-evident, and then just say, oh, by the way, that's a bunch of Z's.
Behold.
Yeah.
I also just thought of an example, or based on the example you're doing right now, like where the triple intersection thing does matter.
All right.
So if you just have a sphere and you puncture it in 3 places, maybe you imagine them being on the equator or something to make it easier. And you can imagine kind of having like 3 different like thirds of the sphere where 2 adjacent ones just intersect in a contractible thing. But all 3 intersect in this like little piece in the top and this little piece in the North Pole and little piece in the South Pole. So the triple intersection is not path connected.
Oh, I see what you mean. Okay. So you mean like you have like this guy, and then we have maybe this guy.
Yeah. And if you just applied then Kampen naively, it would tell you that the fundamental group was like a threefold free product of Z's, but actually it's just a twofold free product of Z's.
Right. So I guess that's, yeah, I think that's right. Because you need the 3 intersection to show that the kernel is only those things and that you don't actually have more things there. So I think you're right. Yeah, that does work. Okay, the last problem I want to do today with you guys is one from Hatcher. I'm going to try to pull up the problem number. There are some other problems on Van Kampen's that are like from the exam that I could give you, but I don't think there's like discussion worthy. And I'll just write those down for you after this. So, okay, this is Hatcher 1.2.7. Let X be the quotient of S2 obtained by identifying the North Pole with the South Pole. Put a cell structure on X and use it to compute pi 1 of X. So I want to note this is not the quotient of every point by its antipodal point, which will give you a real projective space. You're only identifying the North Pole with the South Pole, not any other points. Just draw the shape. Anyone have any ideas for this one?
I greatly appreciate that all 3 of us, after you said that, went like this, went like that, or some like variant of that. That was very interesting. Yeah.
Mm-hmm. I think there's a kind of geometric way to see what it probably should be, although proving it is what you think it is. You need the cell complex structure. I
mean, could you just start with the like usual cell decomp of a 2 sphere, the one such that like the 1 sphere is a subcomplex, and
so you start with this guy, and then maybe here's a 2 cell, there's a 2 cell, that one. Yeah, and then I don't know if that works, but it actually does work, but you need to be a little careful. So you're saying just identify those 2 points. Sure. Yeah, so this turns out it does work. Although personally, I'm not 100% convinced that you could just say, by the way, this is the topological space in question. But Ilan seems to say that you could just, say, oh, by the way, this is obviously the space. So I guess I'll just roll with it. But anyway, so the graph you would get now is your graph is generated by A and B. We have our figure 8. And we have a 2 cell that's, 2 cell on Well, I guess in our original picture, this would be A. This would be B. So I guess our two cells on A, B. And we have another two cell also around AB. So I guess we don't need to write that again. Actually, I think this is maybe easier if I write this as AB inverse. So if you wanted to compute this fundamental group, what would you guys get?
Z.
Yes, it is Z. So the way to see that is that, remember, if we have this relation, the boundary of our original two cell that was attached to the border of our circle, it is now attached to this loop in our figure 8 that goes around like AB inverse. So now our fundamental group is like AB such that AB inverse is the identity, which means that AB inverse equals E. It's equivalent to A equals B. So this becomes just the free group generated by A, which is Z. And again, I'm not 100% convinced you can just quotient the one skeleton and get the same space that you want, but I guess it was obvious enough to Avon. So, and this was also not a qual problem, so maybe we don't have to worry about it.
Good question.
Yeah.
Why do we need? It's entirely possible this is a misunderstanding of cell complexes on my part, but why do we need these sides A and B? Why can't we just, like, we have our sphere, we kind of stretch it out and attach it at, like, to itself at one point. Couldn't we just take like one edge and then connect this two cell from the edge to itself? Or is that not how that works?
I think you could maybe do that, but I need to understand what so what exactly is your cell structure look like?
Like just a point and an edge to itself. And then, like, if you just took a two cell that like started at that edge and then looped around to itself. Does that make sense at all? I don't know if these are the correct terms to be, or like, is this how these are actually built up or not, but.
So something like this?
Yeah. Where it's.
Okay.
Yeah.
I have a harder time visualizing it, but supposing you did do that, I think you get the space. Okay, fundamental group is A. Your relation would be, I think, A inverse. So that relation doesn't tell you anything. So I think you still get Z, supposing that that's a correct structure.
Yeah.
I guess I'm thinking
also this. Yeah, go ahead.
I was just saying, I think I'm imagining Matt's thing is like, if you had like this eye shape, like on a piece of paper, and you like glued the like edges of the eye together or something. So your two cell, that like tells you how your two cell is attached to this one cell or something. And then you just like push the two endpoints together.
Does it make sense to just think of this as like kind of, I guess it almost looks like a donut, but the middle's filled in, and you can just take the cross section of it looks like that figure 8. This is correct. So then the 0 cells that point, and then you're attaching two circles, and then you can attach like a disk to each side, I guess, but where the boundary is that figure 8, like the A, B inverse. Is that what you're doing?
Yeah, so this presentation basically is, I think, what you're saying, where we have our figure 8, and then our boundary goes along A, B inverse.
Okay. That's what I thought.
Okay, the donut description actually really helped me to see what you did originally. So you like took the sphere and you like squished the top and bottom down.
Oh, yes. So that's another way to see that this construction kind of works. But yes, it would look like.
Okay, I was imagining
like that.
You took your sphere, kind of like stretched out into a sausage, and then like wrapped it around and attached it.
Yeah,
and
that's
then
what I
you
have
just
drawn
followed,
here.
I don't know, like the seam of the sausage or something. If that had a seam.
Yeah, any of these like visualizations I think are valid in terms of like thinking about it. But I think you need the cell complex structure to actually prove that this fundamental group is Z and not some other thing. But yeah, I think these shapes are all fine ways to look at it.
Cool, cool.
I have to head out, but thank you. This was really cool.
Yeah, for sure. Let me just write down some of the other problems on fundamental groups that are like on the qual. So Elon gave me a big list somewhere. And some of them were maybe not that helpful, but the other ones were, okay, what did we go over? This was 1.2.7. We did 16.8, we did 15.8a. So the other ones are S16.7 and S18.7. And there's also a Hatcher problem 1.2.4, but this is essentially the same problem as the qual problem where we had all those lines cut out of 3D space. So maybe you don't need to do that again. Link that allows you to collaborate on the YouTube.
I didn't mean to send that yet. I was just pasting it there before.
Oh, well, I'll keep it there. Anyway, these are another 3 problems you might want to look at. And I have the answers for these if you wanted to like check in with me, and Elon does too, of course. So I guess it's been 2 hours and 8 minutes. If you guys have any other questions, I can stick around. Other than that, thank you for coming.
Yeah, thanks. I think I have an idea for this like sphere thing again. Like instead of trying to visualize collapsing, you can maybe just draw a line from the North Pole to the South Pole. And that thing you added is an interval, and so it's contractible. And when you quotient out by something contractible, it's a homotopy equivalence to the original thing. So like,
so you're just
like
saying shrink this red line?
Yeah, basically. So you can just kind of visual like that. And I think it's kind of not that bad to, if you have a CW pair, you can write a cell decomposition of its quotient in a pretty formulaic way, where you kind of just like, literally like kind of just delete all the cells that are quotiented out. And this only works if it's a CW pair. So like, if you can find some cell decomposition of the sphere where like this interval is a subcomplex of like the one skeleton or something, then I think you can get a cell decomposition pretty quickly.
All right, I think that works. Yeah, I was actually stuck on this particular one for a while because I couldn't convince myself that I had a cell complex that I think works, but I couldn't like prove to myself this is actually the same space. So I had to ask Elon to like confirm that this is the space I think it is.
Yeah, I guess you could also say like 2 points you can view as like opposite points on the equator. And then if you, because I think the original cell decomposition that we did with Jacob in like week 1 or something for spheres had each like codimension 1 sphere as the equator as like a subcomplex. It's like S0 is a subcomplex, S1 is a subcomplex, S2 all included as like the equators. So I guess maybe that would get you a cell decomposition too, by just kind of also doing the same quotient thing.
Probably works, yeah.
I also need to head out. Thank you for this. It was very interesting.
Yep. All right. I'll hold on. Does anyone know who's going next week?
That's me.
Okay.
Nice. If you want to post the recording on YouTube yourself, the link in chat will let you collaborate on that playlist, so you can add it to it.
Okay.
Otherwise, if you need me to do it, I can do it. But yeah.
All right. Maybe I should stop the recording now then.